study looked at the relationship between low birth weight and IQ. A random selection of 17 low birth weight children had an average IQ of 95.5 points with a standard deviation of 16. A random selection of 19 normal birth weight children had an average IQ of 104.9 points with a standard deviation of 14.2. Use a 10% significance level to test the claim. So we want to test the claim that the two groups of children have the same average IQ. Same average IQ. Okay, so we're basically saying that the two groups are identical, and they want us to not assume equal variance. So do not assume that we have equal variances in the problem. All right, so first step we're going to do, since we know it's a hypothesis test, is to express the claim symbolically. Okay, so test the claim the two groups of children have the same average IQ. That means the mean for the first group is equal to the mean for the second group. And of course, the two groups are low birth weight and normal birth weight. So you use L and N as subscripts. HO, HA. For the HO, we're going to say that it's the same as the claim because the claim has an equal sign. And whenever it has the equal sign, the HO and the claim are the same. Okay, for HA, we have to express the opposite idea, which would be not equal to here. So we'll say not equal to. So the mean for low birth weight children is not the same as the mean for normal birth weight children. Then we're going to write down the data. So for the data, we'll list the first set under L and the second set under N. Low birth weight, we'll have N, X bar, S, N, X bar, S for each group. And then, of course, we'll have a level of significance alpha for the problem. Okay, so let's start with the N for the first group. A random sample of 17 low birth weight children. So 17 is the N. Had an average IQ of 95.5 points. With a standard deviation of 16. A random selection of 19 normal birth weight children. Had an average IQ of 104.9. With a standard deviation of 14.2. And a significance level of 10%. Okay, so at this point, taking that data, we're going to plug it into our test statistic formula. Since the n's are small, we will go ahead and use a t test stat formula. And the formula for a problem where we do not assume equal variances is going to be x bar L minus x bar for n. Then we'll have the square root of, and under that we'll have the standard deviation for the first group, so standard deviation for group 1 squared over n1 plus the standard deviation for group 2 squared over n2. Then after that, what we're going to want to do is to take that data and plug it in. The data here for the sample mean for the low birth weight group is 95.5 minus the sample mean for the normal birth weight group, 104.9. The standard deviation is going to be 16 squared over 17 plus 14.2 squared over 19. All right, now once we have that, our next step is to go ahead and work out the answer based on that information. So we'll have 95.5 minus 104.9. And then we're going to take that answer and we're going to divide it by the square root here. So square root of 16 squared divided by 17 plus 14.2 squared divided by 19. Close up the parenthesis, hit enter, and we end up with a test stat of negative 1.86. Negative 1.86. Okay, with that test stat, what we're going to do is now plot it on a curve to see how it lands where it lands compared to our critical value. So the curve here, since it's a t-test, looks like a bell curve, right? And because of our alternative hypothesis having the not equal to sign, it'll be a two-tailed test. Okay, and then what we're looking for here is the t critical value. Now, because alpha is 10%, and we're splitting it into two tails, each tail will have 5%, and the degrees of freedom, that's more complicated here. We actually have to work that out using the very difficult formula that we use whenever we can't assume equal variances and the sample sizes are not the same. So that means we have to basically resort to this technique, right? So we're going to have to calculate an A and a B, and with those A and B values, we're going to plug it into this complicated fraction. So we're going to say, let A be equal to the first standard deviation squared, divided by its sample size, which would be 17. And then for B, we will have the second standard deviation squared, divided by its sample size, which is 19. Okay, so let's see what that ends up giving us. So we'll have 16 squared divided by 17. That gives us 15.0505888 ... right? So what I'm going to do is store that in A in my calculator, right? So again, the answer is 15.05888, so on, right? And then for the other one, we're going to do 14.2 squared divided by 19. Hit your answer there, and we get 10.612 ... right? And I'm going to store that under alpha B in my calculator. So I've stored these under A and B, and now I'm going to plug them into this fraction in my calculator. So I'm going to start out with the parentheses and do alpha A plus alpha B. Now, of course, if you don't have a store feature like this where you can plug them into A, B, you simply type in these decimal numbers and give it a few decimal places so that you don't end up introducing any rounding error, or at least you don't introduce too much rounding error. Close the or divide here afterwards, after you close the parentheses and square, divide, and then put in those fractions. So it'll be alpha A squared divided by n minus 1. Now the n for the first group is 17, so we'll be putting in 16 there, plus b squared. B squared is that value. I have that stored in my calculator, and we're going to divide it by 18 in this case. All right, close that up, hit enter, and you get the answer 32.2. So the degrees of freedom finally are just going to be 32, because remember, we truncate the answer here. We remove the decimal portion of the answer. So just 32 is what we'll use. Okay, so now we're going to go to our t-table and finally get our critical value. We're going to look up 0.05 under 32 degrees of freedom. And from there, we'll come up with our two critical values. Okay, so we're looking for 0.05 and 32 degrees of freedom. That's down here at 1.694. Okay, so for our critical value, we found the value 1.694 and negative 1.694. Okay, now at this point, we put our test stat on the curve where it belongs, and you can see that this is actually going to be to the left of 1.694, and so we end in the rejection region. So this will indicate that we should reject HO and support HA. So our initial conclusion is to reject HO and support HA. All right, now from there, of course, we look at our claim and realize that our claim is HO, so we're required to reject HO in this problem. So we're going to say the sample data allows rejection of the claim. Allows rejection of the claim. And of course, you fill in the claim, and the claim would be here that the two groups have the same average IQ. And that's it.